to section 3 of chapter 2 on LU decomposition. We just talk a little bit more about some details about this particular way of factoring a matrix to make the solution of the linear system based on a coefficient matrix A lot easier. It's important to remember that you can take any n by n matrix, any square matrix A, and factor it in the form L times U, where L is a lower triangular matrix and U is an upper triangular matrix. That is nothing to say about whether it's singular or non-singular. You can produce that factorization for any n by n matrix. Now there's different forms of this LU factorization, different ways of standardizing it that have been done, certainly in software. And a couple of them are listed here. One is called the Doolittle form. And the Doolittle form of the LU decomposition is such that the diagonal elements of the L matrix are exactly 1. So we're looking at a particular factorization where we want the diagonal elements of L to be strictly 1. The Kraut formulation is similar, it's just that the 1's lie on the diagonal of U rather than L. And then there is another special case of LU that actually is called the Cholesky decomposition or the Cholesky factorization, which we actually will talk about when you actually have a symmetric matrix A. Because it's symmetric, necessarily then L would have to be equivalent to U transpose. Because again, if it's symmetric, then that must be the case. Just to illustrate what I mean by that is if the matrix A is symmetric, then we know that A has to be equivalent to A transpose. So if we have this factorization A equals LU, then LU quantity transpose has to be the same thing as LU. So that's why what we really have to have here is that we're factoring A. In this case, the L would have to be the same as U transpose, so it would be U transpose U, because if you take the transpose of U transpose U, what do you get? U transpose U. So in a sense, that just says A is equal to A transpose. Now, in asking the question, well, again, if you have the LU decomposition of a matrix, how would you use it to solve a linear system where A is the coefficient matrix in it? We already know the answer to this, of course. We know that if you're able to produce the LU decomposition, you can then replace A by the LU factorization, and then with a little reordering, that's equivalent to L times UX equals B. And we know what we must do then is make a substitution here, call that vector Y. We do forward substitution to solve for Ly equals B, and then do backward substitution. Given the Y as a right-hand side, we would solve Ux equals Y. That is how you would solve the linear system if you have an LU factorization available. One reason why Doolittle's decomposition is commonly used is because we can exploit the fact that the diagonal elements, in this case of the L being all 1, in terms of the storage of the decomposition. So again, with Doolittle's, we would know that the diagonal elements of L, the lower triangular factor, are all 1's, so we don't really need to store them. So what's illustrated here for a 3 by 3 case is how, if you had the factorization, it could be stored in a 2 by 2 array, and actually could be overridden on top of the original storage of the array A if you wanted to. And what you could do is you could store the upper triangular matrix over the upper triangular components of A, and then what we store are the multipliers below the diagonal for L down here, because we don't need the diagonal of L because we understand they're all 1. So the L21 and the L31 and the L32 elements in this case are actually those multipliers that we use in the row operations to zero out those elements. So it's a really nice compact formalization. And I'm going to show you the code, the LU decomp Python code it's on page 47 of the textbook. Also, we'll make it available on Blackboard so that you'll have it available to use, just to sort of illustrate how the storage is economized in this particular form called Doolittle's decomposition. On page 47 of the textbook, the LUDecomp module is given. And again, I will make this available online for you. But I just wanted to point out some of the features of it. It's a very compact little code that will produce the decomposition of the matrix A and then also use it to solve a linear system. So as illustrated, here you can see the docstring module at the very beginning. It's a module called LUDecomp, and you can see that it's going to do the decomposition of producing an L and a U factor from an input matrix A. And then also illustrated in the docstring is the idea that you can then solve, if you had this decomposition in the stored in the array A now and a right-hand side B, you could produce the solution X. So LU solve is getting the factored form, L times U, stored in that array A. That's produced from this call. Now what's interesting here is notice that the input here and the output are the same, which means you're going to input the coefficient matrix A and then override it. When it's overridden with the LU, you're going to return that. So if you needed to store the original AA, you needed to make a copy because it's going to be overridden. So again, this is using NumPy. Here's the definition of the function LUDecomp of A. We need to get the length of or size of the matrix. We can use the len function to do that. And then just with a very straightforward doubly nested for loop, this is pretty much our Gauss elimination code that we had before. You've seen this before. It's exactly the same. The only difference is again, we're overriding on top of A the L and U factors. All right? And this is where the L is the lower triangular elements below the diagonal are being stored. It's those lambda, the multipliers here that are, remember, the element we want to eliminate divided by the pivot element. That'll be stored there. Then also down here you'll see the LU solve module. This says that if you had the LU, I'll do a forward and a backward substitution with it. And so to illustrate it is both parts are done here below. Two for loops are used. The first for loop that I'm pointing to right here would be the lower triangular solve. So this is the forward substitution, and we're using the right-hand side vector B to overwrite to essentially use it as the y vector we had before. And then down here at the bottom, we're going to override it again and produce the actual solution vector. In both cases, we're using dot product function from the NumPy library. So this is the forward substitution, this is the backward substitution. It's not necessary to rewrite this code, it's available for you to use. Just wanted you to make sure you understand, because we've done the derivation of how forward and backward substitution is done. We did that for the 3x3 case, but this is a very general code that's going to do it for the n/n case. It's very compact, and now you can solve any linear system you want by first factoring the matrix, and then you can call the LU solve routine, function as many times as you need using that same LU factorization, but perhaps with a different right-hand side B. Now the Cholesky decomposition, I mentioned this before in our little table before, that is a form of LU in the case that the matrix is symmetric. Formally, the way we would write the Cholesky factorization is as illustrated here. We would write it in this form, that we would take the symmetric matrix A as the product of a lower triangular matrix times an upper triangular matrix, but in this case, the upper triangular matrix is just the transpose of what we had with the lower. So it is important that the Cholesky decomposition exists, of course, if the matrix A is symmetric. That's important. But there's another important property that has to be valid for this decomposition to be computable, and that is that the matrix A must be what we call positive definite. Right? And we'll see sort of an issue where this idea of positive definites comes up in the derivation. But from a formal mathematical statement, positive definite means that if you were to take this quadratic form of any vector that's non-zero, and take the inner product with, a times x, and then take that inner product with x transpose, this x transpose ax is going to be a scalar. Why? Because a times x is a vector, and then we're taking an inner product with that vector with x transpose. So that x transpose ax will be a scalar. And that scalar will always be positive. That's what it means for the matrix positive for all vectors x which aren't 0. So clearly if the vector x was 0, you would get equal to 0. So we're not interested in that. We're saying that if you take any non-zero vector, this quadratic form, x transpose ax, will always be strictly greater than 0. So if we took a matrix that, this is a general matrix, 3x3 matrix here that I've listed and indexed it appropriately, you can see that, I've got 3 rows and 3 columns. For the Cholesky factorization, here's the form. There's the L and there's the L transpose. So notice that the indexing matches. If this is the first column of L is the same thing as the first row of L transpose, the second column of L is the same as the second row of L transpose, and so forth. So for a symmetric matrix, this is possible, because if this truly is symmetric, this A21 element is the same as the A12 element. A13 is the same as A31, and so on. All right? So this is a particular case where the matrix is symmetric, and this does come up in many scientific applications. There's a lot of natural symmetries that exist in geometrical structures and so forth, and mechanics. So it's with meshes and grids, it's very common sometimes for the matrix to be symmetric. If we took that L factor and the L transpose factor we have in the previous slide, and we were actually to do the multiplication, this is what you would actually get for that product of L times L transpose. So that's an illustration. That's an illustration of L times L transpose, and I'm setting that equal to A. So I'm trying to match what the elements of A to the elements of this product would look like. So if we were just to take for a minute and look at the first column, what we notice is that, well, it's interesting that what we're seeing is that A11, of course, is equivalent to L11 transpose. So we're trying to see how would you get, what relationships exist between L and A. Well, clearly what that says is that the diagonal element is the square root of A11. Okay? So that says something about what restrictions there might be on the diagonal element, for example, of A. For this to be real valued, that cannot be negative. So that's something that will come to be important for all these diagonal elements. You can look at what A21, the relationship for A21, must be L11 times L21. Again, I'm just matching terms, that this therefore must be equal to this. All right? So that would say necessarily that L21 then must be your A21 element divided by that L11. Again, how did we get L11? We took the square root of A11. So immediately we can see how we would derive the second component of the column of L. I'm just going down that first column of L to see what the relationships with A would be. And then finally A31, just from pattern matching there, would have to be L11, L31. So that would imply then that L31 is just the A31 element of the original matrix times L11. So what does that tell us? If you can get the square root of A11, I can tell you exactly what the first column of L should be very, very, very quickly. All right? And Cholesky is a very quick algorithm and exploits the symmetry. So that's the first column. having determined the relationship between the first column of L to the original matrix A, what I'm showing you here is how would you get the relationships for the second column of L. And again, all we're doing is we're just matching up the elements of how is A22 related to the factored form of L transpose, and that equality is given here, which would imply if you were to solve for L22, you would need the square root of A22 minus L21 squared. Again, we've already got the first column of L, so this element is known. Again, like we saw with L11, we're having to take a square root, and if that quantity A22 minus L21 quantity squared, if that subtraction produced a negative number, this factorization would fall apart. Similarly, L32, you would equate this particular form to A32 would be matched against this element here, and you could then solve for L32 and show that if you had all the components, if you had just computed L22, you would have everything that you would need to do to derive L32. So again, it just shows you how we could produce an algorithm to derive L given the matrix A, and all we would need left is to get the third column of L. Since there's only one element left to find in the third column of L, because it's a lower triangular matrix, remember, so there's only one element at the bottom that we would need to get. So for the third column of L, we would match up A33 with this last summation there, so A33 would have to be equivalent to the sum of these following squares, L31 squared, as we see there, plus L32 squared, plus L33 squared. And then, of course, if you solved for L33, the last element of L that we're looking for, it would simply be the square root. It would be equal to the, having a little problem with the marker there. It would be simply the square root of A33 minus these other squares, L31 squared. Maybe I can move this up here just so we can see it. I guess not. What we would have is L31 squared minus L32 squared. So all of that would be under the radical, and again, you would have already determined L31 and L32 from previous computations of the second column and the first column of L. So now the L factor would be completely determined. In other words, that we would have been able to determine L11, L22, L33, L21, L31, and L32 here. Okay. So the lower triangular matrix would be fully determined because keep in mind the other elements here are all zeros. Okay, that's just a mistake there. So those should have been on the same row. So if we were to generalize the process that we just reviewed, if we went to the next slide, you can generalize the steps that we were just doing for the 3x3 case with this very simple algorithm. Here is the procedure to derive the diagonal elements of L, and here's the procedure for getting all those off-diagonal elements. If you just looked very carefully, you could go back and match all the computations we were just doing for these particular iterations, and you can simply do these summations as simple loop structures in Python. And I'm going to show you the nice Python module called Cholesky.py from page 50 of the textbook that essentially will now compute the Cholesky decomposition very much according to these two loop structures that you see there. Here is the Cholesky module, which illustrates from the doc string how the Cholesky decomposition is computed. Similar with LU-decomp, it's going to take the symmetric matrix on input, and all it's going to return is the L factor. Remember, since the other factor is just L transpose, you only need one lower triangular factor now to fully determine the Cholesky decomposition. So the Cholesky function basically will take the A and produce on output the L. There's a Cholesky solver or solve, Cholesky solve, SOL function that's going to take that factor L with the right hand side B and then produce the solution for AX equals B. So this is still solving A equals B for the case that the matrix is symmetric and positive definite. After your appropriate imports with an external error function to report a potential error that's going to be captured, which is going to basically relate to failure to get the square roots, positive or zero square roots, and then using math, built-in math module, and NumPy. So here is the beginning of the Cholesky factorization. Again, the symmetric matrix comes in, we get the order or the size of the matrix from the len function, and then we're going to try to compute each column by column the L factor. And notice that because we have to take the square roots, if you go back to the simple computation we did the 3 by 3 case, we have to compute square roots of the diagonal for the diagonal elements, and that's why we have a try block here in Python, an attempt to get the square root. This is continuation. That's what that backslash means. So we're going to get a square root and then subtract the appropriate dot product. If we fail at that, then we're going to capture a value error and then have an external function error that basically just prints out a string. That's what it would do. In this case, it'll print out matrix is not positive definite. And I will provide you this error function as well if it's not available. And provided you can produce the appropriate square root, then you can compute the rest of the column appropriately using this particular for loop. All right. And then what this is going to do is at the very end is we're going to zero out all the components above the diagonal. So we're only going to produce we're going to return the matrix of the array A, which has just the lower triangular matrix form there. So it just has L in it. What comes in is A, what comes out is L. And then at the bottom here is the solver routine that then takes that L and basically does the appropriate solves using L and L transpose. So again, it does the forward substitution with the L, and then it does the backward substitution with L transpose. Now before we would have U here, it would be UX equals Y, but it's essentially the same code. It's just we use the L array now because we can get U by just considering just reversing the direction instead of going down, where we would go across for a row of L of U, we'd be going down a column of L because L transpose is equal to U in this case. So it's just exploiting the fact that we know that U in this case is just L transpose. So this code is pretty compact. It can therefore solve any symmetric positive definite linear system that we have. And I'm going to illustrate now some of the code and how it would produce the factorizations, as well as do a sample problem out of problem set 2.1. I'm actually going to show you problem 16, just so you can see the code of how it works. So here's the example 2.8 code. The example 2.8 is given on page 54 of your textbook. Again, I'll provide this code for you as well so that you could just go to your interpreter, run it a few times, and get familiar with how Cholesky works. It's fairly simple. You'll notice that a couple of import modules, I'm going to import the OS, or the OS module here, just to show you some nice little features, for example, of how to clear the console screen. I'm going to use NumPy, import some particular functions that I need, as well as from the Cholesky code, Cholesky.py module that you need. I would import the functions from it. Again, I'll provide that to you as well. So again, here's just an illustration of, first of all, calling the system command to clear the console screen. It's kind of a nice little handy thing to do. I'm just going to build a nice little 4x4 symmetric matrix here from 4 lists. And again, notice I'm inputting into the array function that NumPy provides you, and it will take each list and build it as a corresponding row. Also, the way I've typed this, you can see the matrix is in fact symmetric. And then if I want a copy of this this matrix A, I'm going to use the .copy function that that's provided with an array structure from NumPy, because remember, when I call Cholesky and I give it this array, it's going to overwrite the array with L. So it's everything above here will be 0, and then this lower triangular part will have the L factor in it. So A will be gone. So that's why I'm making a copy, and I'm copying it into an array called A_old. And then just to illustrate that L times L transpose is in fact A, I'm going to use the dot product function that will basically do matrix multiplication for me here, and multiply L times transpose of L. Notice again there's a built-in function to do transposition, which is very nice in NumPy. And so I'm going to print what A is. I'm going to print L, which comes out of the output of Cholesky on A. And then I'm going to just check and do L times L transpose and print that out as B just to see what it is. And then another thing we could do is, if we want to compute the norm of the error, we'd like to see, well, how far away is this L times L transpose from the original A? So it's a way of just sort of seeing what the error is in computing the Cholesky factorization. Haven't solved any linear system here. I'm just trying to see that, well, if I'm supposed to get this L factor, and L times L transpose is supposed to be the same as A, let's just see in fact how close it is. And then of course just a prompt to ask the user to press return to exit. I've got the path to Python 3 that's available on my desktop here, so all I need to do is just type it, and you can see from the screen I've already run it before, but I'm going to run it again, and nicely clears the console. Prints out, remember, the original matrix A. You can see the lower triangular matrix L that gets produced, and then I'm going to multiply L times L transpose, and on face value it looks pretty much the same as A, but of course there's a little bit of round off errors, but as far as double precision, getting almost 16 digits of accuracy, the error in decomposition is very reasonable. So the routine works perfectly well for us, and I hit return to exit. So that's an illustration that is in fact doing the correct factorization of the symmetric matrix. Now I want to show you one other code that might be a nice illustration of using a Cholesky. It is the 16th, it's problem 16 from problem set 2.1. So I'll share this code with you as well on Blackboard, so you will have all the codes that I demonstrate in lecture available to you on Blackboard. So here's a particular illustration of that problem where the illustration here is to be able to use the Cholesky factor and then solve a particular problem using it. And here again is just using NumPy and using the original Cholesky factor. So here's a solver. Again, it was illustrated in the book, but here's just me creating another function called solve, which basically will solve Ly equals b, and then follow with L transpose x equals y. So again, Ly equals b is what we've always been doing for forward substitution. It's just the back substitution. There is no u. We use L transpose instead. And so this is pretty much the code we just had before that was in the textbook, and I just created a solve routine for it. And here's an illustration of a 3x3 problem, giving using the array function with three lists here, and this matrix is symmetric and positive definite, and then here is a right-hand side vector b, and so we're actually going to try to solve this linear system Ax equals b using Cholesky. We'll make a copy of A, we'll make a copy of B. Again, we're going to call the Cholesky function to factor L, but here we're going to solve. Using a solver we've created here, we're going to solve for the solution vector x, and you'll notice the way this solver routine has been designed, b will come in as the right-hand side vector, but it's going to come out with the solution vector x. So that's why when I say solve LB, I'm not setting anything equal to it, because b is coming in as an input parameter and coming out as an output parameter. So just calling the function is perfectly fine. And then if I want to see what the solution vector x is, I will use the b array now, because b was used as the input right-hand side, but it's also going to be, as illustrated in this for loop, it's going to be producing the solution x. Okay. And then we can compute the error again by doing the dot product with the original A and the solution minus the original right-hand side. That's illustrated here with the call to the toNorm, the default toNorm that's available in the linalg Python function, and see how well we did. So this is an illustration of how to solve Ax equals b. For the particular case, the matrix is symmetric, positive, definite. So if we were to run this code, the solution vector is simply just 1, 2, 3, and the error is 0. So it solves the linear system perfectly. I will provide, again, all these simple Python scripts for you to use. Certainly they'll be helpful for your homework, and just to get more familiar with how these routines for solving linear systems work.